From a technical spec point of view, we can match centrifuges that cost all the way from $1,000 to $5,000. But this is a tool that requires no electricity, no infrastructure. You can carry them around in your pockets for a price point of 20 cents.
We call it a paper fuge. It's essentially a piece of paper, and we put in small holders for capillaries that we can fill with blood. And we have standard string, and we take two pieces of either PVC pipe or wooden handles, and then you just pull on it gently. As you spin, the disc is rotating back and forth. It's rotating in an oscillatory fashion, and there's a moment when the disc is stationary, and then it starts to unwind and go in the other direction as you apply a force.
With this set of principles, we're able to essentially make a centrifuge that spins all the way to 120,000 RPM and 30,000 G-forces. In the lab, we can separate and pull out malaria parasites from blood. We can separate filaria, African sleeping sickness, separate blood plasma. It is an ultra low-cost centrifuge that's built out of principles of a very old toy, the whirligig.
This is a toy that I used to play with as a kid. The puzzle was that I didn't know how fast this would spin. And so I got intrigued and I set this up on a high-speed camera. And I couldn't believe my eyes. This thing, when you hear the noise, is actually going at 10 to 15,000 RPM. To me, that seemed like what we wanted to actually make a centrifuge.
Before us, nobody had actually understood how this toy works. So we spent a significant portion of this time truly understanding the mathematical phase space for how you can convert linear motion into rotational motion. There's some beautiful mathematics hidden inside this object. There is a value in this whimsical nature of searching for solutions because it really forces us outside our own sets of constraints of what a product should actually look like.
The centrifuge is the workhorse of any laboratory, from diagnostics to biology. And if you build a very essential, a key instrument, then you open up to a whole different variety of applications.
We just got back from Madagascar. We took the tool out to the field to work with health workers, and we're starting a clinical validation trial on a larger scale to share it with the community and the healthcare service providers, get the feedback. So it's a very iterative cycle. There is of the order of 1 billion people around the world that live with absolutely no infrastructure, no roads, no electricity. So for us, the inspiration is to make the simplest possible tools that do the job well, such that you can get them distributed around the world.
For more, please visit us at stanford.edu.